In this video, we will be exploring one of the prominent clustering methods called the k-means clustering method. The information about k-means clustering analysis is divided into two parts, the theoretical part and the coding part, which are covered in two separate videos. Please refer to these videos for a comprehensive understanding of k-means clustering analysis. The k-means clustering method belongs to the partitioning clustering methods. Here, the term partitioning means assigning each data point to only one specific cluster. In the previous video, we discussed hierarchical clustering analysis, which forms a hierarchy by linking similar items together. This means that one cluster can be a part of another cluster. However, partitioning clustering methods, like k-means, focus on dividing the data, and one cluster cannot be part of another cluster. K-means clustering analysis is a method that divides data into k-clusters based on Euclidean distance. Here, k represents the predefined number of clusters. In hierarchical clustering, you don't need to specify the number of clusters beforehand, but in k-means, you must specify the number of clusters you want to create. If you set k to 3, for example, it will divide the data into 3 clusters. Let's take a look at the steps involved in executing k-means clustering. First, we predefine the number of clusters, and in this case, let's set k to 3 beforehand. When we set k to 3, we initially create 3 centers, C1, C2, and C3. Next, we calculate the distance from these 3 centers to all data points and assign each data point to the nearest one of these 3 centers. This process forms 3 clusters, which we can label as green, gray, and blue. After that, we recalculate the centers of these clusters based on the data points that have been assigned to them. This step involves updating the positions of C1, C2, and C3 to new locations. After recalculating the centers, C1, C2, and C3, we again compute the distances between these new centers and all data points. Then, we rearrange the data points by assigning them to the nearest center. Through this process, you can observe that data points that were initially in the green cluster may move to the gray cluster, for example. This process is repeated until the centers of the clusters no longer change. As a result, the final clustering is completed, and the data is divided into the predefined 3 clusters. In the previous slide, we discussed how to perform k-means clustering by predefining the value of k and setting the initial centers, C1, C2, and C3. Now let's take a look at how to set these initial centers and the methods for doing so. Firstly, there's the random selection method, which involves assigning initial centers randomly. However, it's important to note that this can lead to different clustering results each time due to the randomness. Another method for setting the initial centers is the k-means plus method. When selecting initial centers, the key is to make sure they are not close to each other, but are well distributed. K-means plus is a good approach to tackle this issue. It selects the next center as the point that is farthest away from the existing centers, ensuring a more balanced distribution of initial centers. Taking a closer look at this process. First, among all data points, we randomly select the first center, C1. Next, we calculate the distances between C1 and all data points and choose the data point farthest from C1 as the second center, C2. Then, for each data point, we calculate the distance to the nearest center and select the data point that is farthest from its closest center as the third center, which we label as C3. In this way, if we have predefined k as 3, we set up the initial centers like this. In k-means clustering, we mentioned that we predefine the number of clusters, denoted as k. Now, let's explore how to determine an appropriate value for k. Firstly, One method to find an appropriate K is by using the elbow point. In this approach, we calculate the sum of squares of distances between the centers and data points, known as the within-cluster sum of squares, WSS, for each cluster. We observe the pattern of how WSS changes with the number of clusters. Specifically, we look for a point where WSS starts to significantly decrease or levels off, creating an elbow in the plot. This elbow point can help us choose an appropriate value for K. Apart from the elbow point method, another way to determine the appropriate K in K-means clustering is through the silhouette score method. The silhouette score method can be useful when finding the elbow point is not clear-cut. A well-formed cluster implies that data points within the same cluster are close to each other, while being far from data points in other clusters. Therefore, the silhouette score is calculated using the following formula. That is, the difference between B and A is divided by the maximum distance of A and B. Here, A represents the average distance between individual data points within the same cluster, and B represents the average distance between all data points in one cluster to the nearest neighboring cluster. The larger the difference between B and A relative to the maximum of the two, the better the clustering is. Therefore, the silhouette score is a metric that indicates how close a data point in one cluster is to its own cluster compared to other clusters. It ranges between -1 and 1. A silhouette score close to 1 implies that a data point is close to its own cluster and far from neighboring clusters, suggesting good clustering performance. On the other hand, a score close to 0 indicates that a data point is near the boundary between clusters, and a negative score suggests that clustering did not perform well. In conclusion, a higher silhouette score, closer to 1, signifies better clustering. Thus, by setting the number of clusters, K, to the value that produces the highest silhouette score, you can determine the optimal number of clusters for your K-means clustering analysis.